Hello, Physics 20s. I want to go over some of the properties of waves today. This will set us up for some future discussions with something called closed pipes and as well two-source interference. So there really isn't any math with what I want to show you today other than um, kind of some simple relationships with waves. So I released these notes. There's really 5 different properties of waves, and I'll try and highlight the aspects of them that are relevant for you. The first off is reflection. Waves will reflect off of any surface or barrier, okay? And the simplest way to think of reflection is just like this picture shows here. If you shoot a hockey puck off the boards, you do a bounce pass in basketball, the angle of incidence is equal to what we call the angle of reflection. Now, these angles, we don't do any math with this yet, but in Physics 30 we will. This is called the normal. And you might recognize that from some of your math classes. A normal is a perpendicular reference to the surface. When we look at the incidence the angle of incidence, that would be like theta 1 here. That would be exactly the same over here. So theta 1 is equal to theta 1. But when it comes to, say, ropes or springs and strings, for example, it's kind of similar, but it maybe does something you don't always expect. I showed here 2 pictures, and I'll show you an animation here in a second, but if you make a pulse in a string or a rope, and it's hitting a fixed barrier, like it's tied to something, that pulse, when it hits the barrier, the energy will flip the pulse upside down and then it will return backwards, okay? So what that looks like here, if I could just, actually, I'll try and pull this up for you, is, whoops, wrong one, is this right here. So here you can see there's a wave pulse just traveling along a string. I used a bed sheet example if you generate a pulse. Okay, so again, the string is displaced up and down, but the pulse moves from left to right. If there's a hard boundary, though, this is kind of cool with a pulse. When it hits that boundary, it inverts itself. So as this animation repeats itself, you can see it pretty easily. Barring any loss of energy due to heat or anything, this would happen. You would get exactly the same displacement in the downwards direction after it reflects. Okay, that's from a fixed barrier. If it's a soft boundary, then something a little bit different happens, because soft boundary means like it's the end of the string is on a ring or something that's around a pole, and that ring could go up and down. Anyway, in this case, then it would reflect back vertical, so you'd still have a positive amplitude afterwards. These are kind of fun to note as well. Don't worry about the math so much, but if you have two pieces of string or 2 ropes of different thickness, if you send in a pulse from the left here to that interchange, it would be like you're changing the medium, which you are. Some of the energy would get transmitted into the thicker piece of rope, and it would leave with a lower amplitude, though, because some of that energy was absorbed in the transmission from thin rope to thick rope, if you can see that. And there'd also be a little bit of reflection too. So in the thin rope, there's a bit of reflection, but some of the energy gets transferred into the thicker rope. This is the one I really like, though, here. This is like a bullwhip. And there's some fascinating physics that goes on with you when you're cracking a whip. You start with a thick end, okay, like the handle, and you create a disturbance. You create, an amplitude or a disturbance in the whip, and the whip is designed to taper as it goes from the handle down to the cracker, okay, or the tip of the whip. And what's really cool is you can kind of get a sense of what happens here. See, the amplitude dramatically increases in the thinner part of the whip. And also the speed changes. I know it's kind of hard to, we're not doing the math here, but you can see that the pulse coming in is traveling at a certain speed, and then the pulse afterwards travels at a faster speed. So there's really a conservation of momentum here. We have mass and velocity kind of trading places. And this is how you can accelerate the tip of a whip to the speed of sound, which we're going to study that shortly. Speed of sound, yeah, it's about 340 meters per second. We'll learn about the properties behind it. It's pretty close to 1,200 kilometers per hour. So the point is that the tip of a whip actually can get to those speeds using basically generating a pulse in the whip. So that's kind of cool. Anyway, here, let me pull this back up. So that's those are some of the principles associated with with reflection. Now, refraction is all based on the truth that light actually, or light, I should say, anything that travels in waves, so sound waves, light waves, water waves, they travel slower in more dense mediums, okay? And in water kind of has a weird trick because it's actually shallower water that or shallow water produces slower speeds and deep water produces fast speeds. So basically, to keep it simple with refraction is basically what happens when a wave encounters a change in the density of the medium or another change in the medium, okay, whether it's thick or thin. And with light actually refracts. White light will enter a glass prism and each of the wavelengths of light will bend or will refract at a different angle, and this is what causes the scattering of light. And we get to study that a lot in Physics 30. In water and sound waves, which is kind of what we're going to study, if you're traveling in a fast medium at an angle to a slow medium, so I kind of blow this up here a little bit. They show these wave fronts as these dotted lines. I'm just kind of highlighting them here, okay? But as those wave fronts move, and they're moving very fast, we have a fast medium here, okay? So this is like V1 would be quite high here, and wavelength number 1 is large, okay, from here to here. But when we get to the slow medium, and this is very similar to the ripple tank effect, and I'm going to change the color here. Once you hit the slow medium, the waves travel slower. And there's a weird transition here where part of the wave, and I'm doing this on purpose, part of the wave, the red part is still in the fast medium, but the blue part is in the slow medium. So what happens is the wave bends, it like changes direction because part of the wave is now in the slower medium. And so, over that transitionary period, this one only showed kind of one transitionary period, but now the wavelengths are closer together and the velocity V2 is smaller. Okay, so wavelength number 2. Okay, I know that's a little bit, I kind of made that a bit small, but this is exactly what happens when water goes from, this is from deep water, I guess this would be deep here, deep water into shallow water. Okay, and you've kind of seen that already. Now, actually, I have a short video clip of this just happening. There's no audio or anything, but if you can see, you maybe have seen this on a windy day on a lake. If you look at the wave fronts moving in the water, there's deep water in the center of the canal, and then the water gets shallower towards the edges. And so this, like from the side here, you can see it. So the waves here, like you can see the wave fronts moving kind of uniformly in the middle, but on the sides they're curling. Okay, because on the sides the waves are slowing down. So part of the wave is still traveling fast while the part of the wave that's in shallow water is slowing down. So the next time you see water waves, out on a lake or in a river or something, pay attention to the depth of the water, because that will help you understand why there's a curve in the wave, because again, the shallow water, the wave is slowing down in this, and that's exactly what you see. That's actually really cool. So here, let me come back to this. So that's refraction, okay? It's the bending or changing of direction of a wave as it moves from one medium to another, and it is due to the density or the properties of the wave. Diffraction is another really cool property, and again, all you need to know about diffraction is that waves will radiate outwards from a narrow opening, or they will they will kind of wrap or bend around an obstacle. This is showing just the narrow opening. I guess if it was an obstacle, let's say you have an obstacle like this and you have some wave fronts moving towards it, okay, the wave fronts around it will just keep going, okay, like this, but behind it they'll kind of bend and kind of curve back, something like this, okay, until eventually they curve back hardly at all, and then after a while the wave has kind of reformed. So and that was showing it moving from left to right, just like these other animations are. The narrower the opening, the more diffraction there is, because see here, the opening, you can almost fit the whole wave in it in the first one, but in this second one, the opening is really, really tiny. So the argument here, or the theory behind it, is that part of the wave, like maybe you can see this little part in blue that I'm highlighting, that part is unaffected. It just carries on straight through, but the wave then kind of bends around the opening in that concentric circle phenomenon, and the wave will actually radiate outwards in kind of all directions from the opening. So anyway, that's called diffraction. It's another really cool property of waves. What that leads to, though, is another property called interference. We're going to look at this in a couple examples. This is showing two openings. It's a famous experiment. It's called the double slit experiment. We'll learn about it in Physics 30. But you can see that the wave fronts, or the lines, represent crests, and they are crossing over each other. So where a crest meets a crest, okay, that's happening all over the place. And we're going to look at some really cool symmetrical patterns, okay? But where a crest meets a crest, they superimpose. The crests actually add together, and you get an amplification. You get a greater positive amplitude. And the same thing happens in the reverse with the troughs. So interference is another property that waves exhibit. The last one is kind of a cool one, and it's the principle of polarization. I think you guys have all heard of polarized sunglasses or polarized camera lenses. Light is a good way to talk about it, because light actually is, you can think of it as electromagnetic radiation, or vibrations that vibrate in all directions. And if you apply a filter to unfiltered light, then only the wavelengths that are parallel with the filter will pass through, if you can see in that image right here. So the majority of these, the majority of these other waves don't make it through. Just this one makes it through, okay? And obviously, if you set up a second polarized filter, the horizontal one, then you could cancel out the light altogether, and that's actually what can happen. So the Inuit actually have a cool example of this up in the far north. When the sun is shining on snow and ice, you can get what's called snow blindness. Some of you may have experienced it, or at least degree of it. Even when you're driving on a really bright winter sunny day, all that extra sunlight reflecting in your eye, it overstimulates your eye, and it can cause headaches and real sickness. Anyway, the Inuit figured out, they took a piece of whalebone and cut horizontal slits in it. What they were doing was effectively this little trick. They were blocking all the wavelengths of light that weren't parallel with the slit, so only some light was getting through, and that was way more tolerable. And they could easily work outside on a bright sunny day and not get snow blindness. Most of us, though, any pair of sunglasses you have has a polarizing filter on it. And they often say UV filter too, so that filters out ultraviolet light, or at least cuts it down. But for sure, it enables you to see on a bright sunny day. It cuts it down. So those are the 5 properties, okay? Reflection, refraction, diffraction, interference, and polarization. I just want to take a minute further on interference and this idea of superposition, because there's a couple of terms that we're gonna use shortly. So imagine if you send 2 pulses towards each other, A and B. When they meet, what's really cool is they don't bounce off each other. They actually pass right through each other. But in the course of doing that, there are 2 amplitudes. So this would be amplitude from A, and then this would be amplitude from B. And they would add together. And they would make what's called, we're going to use, starting this term, it's called an antinode. Okay, it's an area of amplification, or it's an area of what we call constructive interference. Okay, constructive interference. That's also highlighted here in this picture, constructive interference. And I'll show you that in a minute too. But you see you have pulse A. Pulse A is this one right here. And then pulse B is this one right here. And when they meet, they superimpose, or their energies add together, and it creates the resultant, or an antinode like this. Okay, so those two amplitudes, so here's this amplitude and here's that amplitude, they would add together and make the blue super wave, which is called constructive interference. Okay, now just the opposite, I'm sure you can maybe guess it now. The opposite would be destructive interference. That would be where we sent two pulses at each other, but one was a negative pulse, the other was a positive pulse. When A and B meet, in this case, their amplitudes are the same. So A would have, like, say, a +5, and B could be a -5, or, you know, whatever you're measuring the amplitude in centimeters, whatever. When they meet, those two amplitudes will add together and they cancel out. And that's called a node. Okay, so areas where waves cancel out are called nodes. And what's really cool about waves, of course, is that just happens for the few milliseconds or seconds that the waves are actually interacting, but then they pass through each other. And as you can see here in the diagram, pulse B continues to the left and pulse A continues to the right. In class, if we had some springs, you guys could actually see this, and it's kind of fun to observe. But anyway, here's an example of deconstructive interference. We have pulse A. Pulse A is this pulse here, and it would be moving to the right, and then here is pulse B moving to the left like this. And their resulting wave would be this kind of cross here, because both of the waves would cancel out. Okay, so what's a really cool phenomenon here is something called a standing wave. Okay, and a standing wave occurs when two waves of exactly the same frequency kind of line up. And one way to do this, well, I'll show you a couple of ways to do this, but when they meet, if two waves with the same frequency and wavelength meet, you can kind of follow this pattern, and they actually form an interchanging pattern of nodes, or sorry, of crests and troughs. Okay, and this is the pattern that results. And the simplest way to do this is actually, if you can imagine having a spring, and I'll show you a video of it here in a second, but if you could send like a series of wave fronts from left to right into a fixed barrier right here. Okay, so if that barrier is fixed, if you remember what I showed you earlier about reflection, the waves, when they hit that, they will invert and then they will go back the other way. So on the way back, the wave will do this. Okay, so I just kind of changed color just to separate the two. And the point is, if you keep doing that back and forth, you may have done this with a skipping rope when you were a kid. You have one person hold the end of the other end, and you just kind of vibrate it back and forth. If you do it at just the right rate, you can get the wave. Your skipping rope will be in the blue position, like for 1 second, and then, you know, like a half a second later, it'll be in the red position. And it'll oscillate back and forth from red to blue to red to blue. And it'll happen so fast that you'll see effectively this pattern. You'll see what are called antinodes, which are these guys. Okay, you'll see areas of amplification. Okay, so this whole region in here, you'll see this going back and forth, back and forth, back and forth. But then you'll also see parts of the skipping rope or the spring, whatever it is, that appear not to be moving. Okay, and that's happening right there, right there, right there, and so on. So in these regions here, it's like a little hinge, and the skipping rope is just kind of pivoting on that position. Those are called the nodes. Okay, nodes. So yeah, so nodes remain motionless. The antinodes are the areas of amplification. I'm going to come back to this later when we talk about closed pipes, but for now, what I want to show you is actually I'll show you two things here. Let's try I'll try this one here first, and actually it might make me disappear. Let's see if my computer can handle this without crashing. Here, maybe I come back to this. So this would be considered a fundamental frequency. This is kind of like plucking a guitar string and the whole string moves up and down, okay? That would be kind of the first fundamental frequency. Another mode, though, is where you can get two antinodes instead of just one. And here's one with three antinodes and so on. So you can see the faster you introduce a frequency. So here's one with four. So can you see the areas of the spring here that aren't moving? It'd be the nodes. Then the areas of the spring that are moving are the antinodes. Okay, so that's actually really kind of fun to try in terms of actually recreating it yourself. So yeah, we are going to talk about that shortly. I'll maybe just end on one more thing here. This is kind of a fun application of superposition here. This is called a Fourier wave animation, I guess, and it has a lot to do with a synthesizer. If you can imagine, a synthesizer has the ability to produce multiple frequencies, and if you overlay them, you can get different sounds. So if you can see here on this animation here, I'm controlling essentially one form of a wave here, okay? So, and they're called harmonics if you can see them, and I can change the amplitude. So this is like, I'm just simulating a standing wave where I'm getting two antinodes here, okay? Now in the bottom here, it says sum. This is showing the sum of all of the waves that I'm inputting. So I'm going to input a second wave. Now look at this. See, this second wave actually has double the number of antinodes, okay? But the bottom is showing how those waves superimpose on top of each other, okay? And effectively, look, I can almost make parts of the wave cancel out. You can look at this here, like I can see, oh wait, I guess I got to go just a little bit more. Yeah, see if I'm kind of in this region here, if you can see where my cursor is, kind of, or maybe I can zoom in just a little bit. Maybe it won't let me. Yeah, so right in here, you can see I have an amplitude positive from the red and an amplitude negative from the orange, and the resulting wave is canceled out, okay? It's canceled out. Whereas here, if this region, you can see I have a negative amplitude from orange and also from red, and those two add together, they actually go off the chart. In fact, I have to make it a little bit smaller to show you that there's a larger amplification there. So what's crazy is you can start to superimpose a whole bunch of waves together, and we could equate that with sound. I'll maybe just try that once so you can hear this. So we'll just add some sound there if you can hear that, and I'll just start adding waves and just you can hear what it sounds like. Okay, I'm having too much fun. So you can see here, look in the center, look at all these waves that have, they're all superimposing on top of each other, and they're making this super wave here, okay? And there's a whole bunch of different configurations. Here's one called Sawtooth. I don't know, these are kind of fun to play with. But you can see though that even in applying waves in a number of different ways, you can actually produce a single wave that's the result, or the superposition as we call it. So anyway, I can have a lot of fun with that, but I won't test your eardrums anymore. So, but yeah, I'm going to post some more math shortly on the application of a standing wave, and primarily in a closed pipe. So that'll be coming. Anyway, keep up the good work, you guys.